where you have some condition that can be checked in some finite radius on a vertex, and we want to meet this condition at as many vertices as we can. And we want to find these solutions by working locally in some sense. For this talk, working locally means that we want to find measurable solutions on the Schreier graph of a group acting on its Bernoulli shift for various March groups gamma. So why do we want to do this? Well, there's a measure here and there's a group, so we're doing measured group theory, and we all love to do that. But maybe you're wondering why these problems, what does this have to do with locality? And I don't really have time to talk about that, but as Felix also didn't talk about, there's some connections with distributed computing that are pretty interesting. Good. Okay, yeah, right. So in short, trust me, it's a good idea. Okay, and one naive strategy for finding these measurable solutions is to take your graph and cut it into finite pieces. And on each of the finite pieces, it's finite, so we can have a selector, so we can do whatever we want. Find some optimal solution there, and then try to piece them all back together in the end. The question is sort of how well does this work? Okay, so one way of trying to measure this, first a bit of notation, right? Brackets V for the connected component of V and the graph G. If I want to be very explicit about the graph, I'll include it as a subscript. And then for a barrel graph G on some measure space, we'll write H K of G as the following. We look at all of the measurable subsets of our graph, of our vertex set. We look at the induced subgraph on it, right? We have, okay, well, I'll use my finger to point. Induced subgraph on this subset. We want to find subsets with this induced subgraph, all of its components have size at most k. Okay, and we want to find the largest such subset. We take supreme over their measures. And notice that because I'm only looking out to, I'm looking at k vertices here, this is one of these kinds of local problems. You can check this by looking out to radius like k+1 or something. Okay, great. And then h of g will be just the limit with k of these numbers. It's increasing and bounded, so it has a cool. So this h number can be read off from the sort of statistics of local statistics of labelings in your graph. Anyway, defining it though, that's maybe a little bit more natural. Okay, so we take a graph and we just look at measurable subgraphs with finite components. I'm going to take supreme over those. It's the exact same thing because you can take this and then throw away epsilon more to get something finite with k size k components. Okay. So it turns out that if you have a group and its k graph is a tree, then a deregular tree, then it doesn't matter what that group was. It'll have the same. The answer will come out the same. And here I'm allowing things like free products of liquid groups over 2. Unlike Ronnie, I believe that those things have Cayley groups as trees. So I can have D, in particular, I can have D be odd if I want, and I often do want. You can also take the Bernoulli graphing built over the modular random graph. That's the Dirac at the deregular tree, but we're talking about groups here, so I want to have a group. Okay, and for those as talk, we want to compute this for various D, or at least bound it. Okay, and maybe something worth pointing out here. I define these HKs, or I define these things under these HKs. These HKs are from the local labeling problem, and there's just a general fact we can invoke here about local labeling problems. That if we have a sequence of random regular sequence of random regular graphs and asymptotically almost surely, its HK number will be above that of the irregular tree. And you can replace random regular graph with any sequence whose girth goes to infinity. So there's some connection between these kinds of problems and asymptotics of large girth graphs. Fun, worth knowing. Okay. So first, let's get an upper bound. For AD, we have this upper bound. The largest finite component subgraph has measure at most d over 2 d minus 1. You'll see this will come from some kind of isoparametric inequality. So proof, let A be some measurable subgraph of finite components. And then while B is notation, and so mu will be a measure on the vertex set, it will also be the measure of edge sets. And the way that we've usually measuring them, we average sort of number of vertices, an edge incident to it in this set, and divide by 2 for some kind of normalization. Okay, so if G is a finite graph, we can counting measure. This is just the number of edges in a set divided by the number of vertices. Okay, so we deregular tree, measure the whole tree. What do we get? We get d over 2. The integrand is d everywhere. We can break this up into looking at edges which stay inside of our set A, edges which stay inside of the complement of A, and then the boundary, the edge boundary of A, so the edges that go in between A and its complement. So we collect these two terms. What is that? That is the number of edges which at least one of their endpoints is in A. And we have finite components, so we can instead measure the expected number of edges that touch the component of A and then divide by the size of the component of A. So we get this nice integral using some double counting arguments and basic facts about trees. Okay, and then this thing is always positive, so we get an inequality. And that's great. And you can divide and get the result. And note that this last line is an equality exactly when this thing is 0. So exactly when the complement of our set is independent.
You mean G, or you swapped G with E on purpose?
Yeah, I mean G, sorry. Yeah. So in the case for D equals 3, we can actually compute this exactly. That upper bound is equal to, we can meet this upper bound, or we can get anything arbitrarily less than it. So H of T3 is 3/4. How are we going to do this? So we'll build some induced subgraph whose complement is independent and whose components are all finite in size at least k. We go back a couple slides. Yep, right. So this will be 0, so this will be an equality, and then we can make this term be as small as we like by ensuring that the integrand is at most 1 over k. Okay, so we're going to control that expected value there, that mean. We're going to do this by doing some kind of careful inductive construction where we control the ends in our remainder graph at each step. I'm going to give a sort of proof by pictures of how this works. Right. So first, let me describe a kind of coloring of trees of degree at most 3. First, we'll color the leaves red. And then once we've colored the leaves red, there'll be some vertices left over who we'll see at most 1 non-red vertices. We'll also color those red. We'll sort of keep pruning our tree like this. So in this next step, this guy should turn red. And if you have trouble seeing red, those are squares. And then once we've pruned away all of the red squares, we're left with something that every vertex has degree 2 or 3. So we'll color the degree 2 guys yellow, circles, and the degree 3 guys green, stars. And we zoom out, and the picture looks something like this. We have these green stars with long yellow paths in between them, and then maybe some red stuff whiskering off. Okay. Note that if G has finitely many green vertices, then we can finitize it by throwing away epsilon many vertices. This is just restating that if a graph has finitely many ends, then it's hyperfinite. Right. So if we do this, if it has some yellows, we can do sort of percolation on the yellows and send the percolation to 0. And if it has reds, then you just do this pruning thing, but you'd be a bit careful so that you only throw away a vertex once you see it has a really huge component behind it. Okay. Cool. So here's how the theorem works. We find for every k some measurable subgraph of some 3 regular treeing so that its components have size at least k. They have finitely many green vertices, and so this complement is independent. And we do this in stages. At each stage, we will isolate some clusters and throw them into A, throw away the boundaries of their clusters into the complement, and iteratively do this in the remainder. So how do we find these clusters? So we look at our graph here. This is some step in the process. we've sort of thinned things out. We have these long yellow paths. And we can think of this as being now just a graph on the green vertices where it's an edge between them are given by these yellow paths. And we take some nice, really sparse set in this graph. And then we look at the k-balls around this very sparse set. And then we make those our clusters, and we throw away things in the boundary. This should also be thrown away, but there's a typo. Okay, right. So things we threw away, they're going to definitely be not next to each other, and not next to the things we're throwing away currently. And then degree 3 in the remainder graphs, they're also not going to be next to things we threw away in the previous iterations. So the complement of the graph we build will be independent. By construction, all of these clusters will have finitely many greens. And at each step, we're throwing away some positive measure set of greens because we can choose large, well-separated sets. And in the remainder graph, we can see that there's always going to be some ends escaping to infinity. So in the remainder graph, we'll still have infinite components. So as we iterate this over and over again, we can still keep making sure that our clusters find enough sets to have size at least k, because each of our components is infinite. We maintain this having ends escape to infinity. And then the limit, maybe there's some stuff left over, but there won't be any greens in it. Okay, so that's a very rapid sketch of how this works. Good. Okay. Okay, so what about these sort of middling Ds? So I'm going to get some upper bounds for it. It'll be, or sorry, some lower bounds for it. We've got an upper bound already. And I'm going to do it using differential equations, which is sort of interesting and maybe not something people would expect to see, this kind of conference. So what's the process going to be? So again, we're going to grow some clusters in our graph and then isolate them. We're going to hope that these clusters are going to be big and make sure that they're finite. And what we're going to do them is at each stage, we do some operation in lots of places all at once, but the basic operation is at a vertex. Once it's become active, we will look at the ball of radius k around it, but where we're allowed to jump over degree 2 vertices. We don't count those as having any distance. Okay, and then the internal vertices on the boundary we throw away. So again, we're isolating this as a cluster. Okay. So how well does this do? Okay. So okay, maybe I should say also, okay, this is what we do at a vertex, and the full operation is we iteratively do a construction where we pick a sparse set of vertices that remains, pick each vertex IID at random with some small probability epsilon, and apply this operation everywhere at every vertex that we picked at once. And maybe there's some clashes, and if two things clash, then we just delete all of the vertices involved in the clash. And the clashes will occur with probability, if we activate a vertex with probability epsilon, then these clashes occur with probability epsilon squared, and so they sort of won't add up to anything in the limit. So if we let this bold z, this vector z, record the measure of vertices of degree I and the remainder vertex for each I at some stage, we can check. And also we look at the expected change, the number of vertices of degree I made by one of these, by an instance of this operation, given the degree of this starting vertex. Right, so if we go back a bit. Right, so in this case, start here, and we have thrown away a bunch of vertices of degree 2. So degree 2 will go down. We've also made some of the edges. So we count how many we throw away, we subtract that, add how many we created at the boundary, add that, take the expected value, this count over all of our vertices. That's what these deltas are. Okay. Then at rescaling time, we can check that we get this difference equation. The total change of each of the vertices, the measure of vertices of degree I at each step is given by the same what probability to activate epsilon, what probability to activate a vertex with degree j, how many vertices in degree I does that vertex create, something that plus some epsilon squared error. Okay, going quickly the sketch, but okay, something is coming through. And then letting epsilon go to 0, this looks like an Euler approximation to a differential equation. So we can use MATLAB to, or other numerical software is available. We can use some computers to integrate these kinds of equations. Right. So I meant to have, I wanted to have one of these cockroaches on this slide, but if you Google latex cockroach, you don't get fonts for some reason. Okay. And also, I suppose I should say, we can track the size of the output by adding another variable, adding some more terms in our differential equation. So I don't have time to go through the derivation of this stuff, but for our algorithm, we can compute all these things and we get this horrible mess. It is what it is. Trust me. And then we can plug all this into a computer. We can get some numbers. So for d 3 to 6, we can get the upper bounds and the lower bounds on this finitizing number. Upper bounds, finite fractions. Lower bounds, we know it is 3, and then we get some numbers like this. Kind of neat. Excited to have numbers. It's fun to try to optimize and make the numbers get bigger. I encourage you all to work on this kind of thing. Great. So that's sort of I've done so far, and there are lots of things to keep working on. So some further questions. Okay, so if D is very large, we can get some bounds by comparing to independent sets. Okay. If you have one of these finite component subgraphs, then each component you can two-color. And so the size of an independent set, the optimal size of the largest independent set is at least half of this finitizing number. Or they're saying that finitizing number is at most half of the size of the largest independent set. So as D goes to infinity, there are some known very good bounds for independent sets and random regular graphs. For factor of ID independent sets and trees, D over, say, log D over D asymptotically. And of course, an independent set is a finite component subgraph, so it also gives you a lower bound. So we have these two upper and lower bounds for very large D asymptotically. And if you can do better, maybe comparing to some other sort of local labeling problem can give you a better upper bound, or improving techniques with local lemma, you can get better lower bound, or trying more direct entropy arguments for this coloring bounds. Lots of interesting things to try here. We also ask, what can we do small d? Can we do better? We should have better differential equations or techniques that don't involve differential equations. Okay. And then more generally, sort of what the relationship between these sort of large growth asymptotics and graphings are. I handed out earlier, there was sort of, we could compare random regular graphs to the factor of ID processes, the measurable labelings of Bernoulli shifts. But it's unclear if there is, for instance, a particular graphing that exactly tells you, that has exactly the same local statistics as what random regular graph should limit to. What?
Same local statistics as what?
Right. So you can look at the local statistics of a random regular graph. It's open if these all converge to the statistics of some graphing. Very interesting question, and there are a billion other questions in this thing. But yeah, I'll talk. Yeah.
Why did you only go to 6? It's MATLAB.
Yeah, because MATLAB. Yeah, I can't plug in Infinite. Sorry, my ear fell off. I can't plug in Infinity into a computer yet.
How about 7 though? Did 7's too much for MATLAB, or what's the deal?
Well, 7 is too much for me to took too long for me to type in. I got hand cramps. Yeah.
If you check the random regular graphs, what you can say there's a bounding the scale, the size of the movement.
Not more than this. I mean, this gives you some information.
There may be some expected value from at least the expected value one might be able to get something, but
Yeah, it's sort of expectation arguments or entropy arguments. Yeah, I mean, that's certainly something worth looking at, and I haven't more carefully than I have here.
Are there any, is there anything general or what, anything you can say outside of the trees? Like, or is the result of this parameter of finding?
Well, it's one, it can only if the Bernoulli shift is hyperfinite.
Okay, nice.
Is there any relationship, is there any numerical relationship between the like isoparametric constant of the graph?
Yeah, if you chase that argument from before, it gives you some inequality.
Give you a lower bound?
Yeah, it gives you an upper bound
An upper.
in terms of isoparametric inequality.
This large group has what's reminded me, we have a joint paper to write from some.
Okay. I mean,
You wrote already.
yeah. Just tell me what to do with it. No?
Okay.
Any other questions? Anyone else have a joint paper with me that they want to talk about?
More questions? So if not, I think I am on the speakers.